Welcome everybody, my name is Ishita Trivedi and I am a student at North Carolina State University. I recently defended my PhD, so I'm in this wonderful time where I finished my defense a couple of weeks ago, but haven't started my new job yet, so anyway, welcome to a video describing my research that I've completed over the past couple of years. This video will walk you through a very high overview of what I have done for my PhD research, and I hope you enjoy.
And now for something completely different.
In 2015, as a new bachelor's degree graduate in nuclear engineering from the Pennsylvania State University, I was looking around to find a project that could hold my interest over the next couple of years as I go ahead and start graduate school at North Carolina State University. Knowing that my true interest lies with innovative technology and advanced research, I decided that I wanted to pursue a project that would fall in Generation 4 reactors. During my research, I realized that Generation 4 International Forum, or GIF, had in fact identified lead-cooled fast reactors, or LFRs, as one of the 6 most promising fast reactor designs. This renewed interest in LFRs around the globe with several concepts. However, the focus of the research around the world was primarily around optimizing core design, or assessing core safety. What we found lacking is an approach that would propagate uncertainties through multiple levels of core modeling to systematically assess its impact on core safety, specifically in relation to lead-cooled fast reactors. So utilizing the BEPU methods, I ended up reaching the topic for my research to develop uncertainty quantification and propagation methodology for safety analysis of lead-cooled fast reactors. My research is completed in 2 parts, where part 1 focused on method development and part 2 attempts to benchmark the methods by applying it on a more mature design. In the first part, a 2-step approach is used to quantify and propagate nuclear data uncertainties through multiple levels of core modeling and simulation. The overall goal here is to understand how the uncertainties originating from some fundamental input quantities, such as nuclear data, impact the core safety once you propagate it through different levels of core modeling, and see how it affects core safety. For a more comprehensive UQ, we add an additional step of sensitivity analysis, where we try to see how sensitive are these temperatures to perturbation in nuclear data. On the bottom block here, I describe the tools that were utilized at each of the different steps. All the tools that I used are primarily Argonne National Lab codes, as well as Dakota, which is from Zendia. In part 2, the method described previously is applied on a more mature design for some preliminary benchmark attempts. Here I selected the Alfred core, which was developed in Europe and has published data that can be used for some comparative analysis. So after some extensive research on both part 1 and part 2 of my thesis work over the past few years, I was able to draw some conclusions. First, we noticed that large uncertainty contributors are coming from the same few reaction cross-sections, such as U35 capture, U38 capture, and U38 inelastic scattering. These are likely coming from the very high original uncertainties of these reaction cross-sections themselves. From sensitivity analysis connecting these core safety temperatures to perturbations in reaction cross-sections, we noticed that the core safety temperatures are highly sensitive to U38 capture cross-section, U38 inelastic scattering, and U35 fission cross-sections. And finally, from the benchmark analysis, where the results from our method were compared to results from another code, such as Scale, the results were in fact quite encouraging, where the largest contributors from both codes were similar for steady-state parameters, where we noticed that the uncertainties were originating from U-238 inelastic scattering, plutonium-239 capture, and plutonium-39 new reaction cross-section. And with that, I was able to compile all of my findings and results into a very large document known as my thesis, and proceed to defending my research.
Well, I hope you enjoyed that very high overview of what I've completed for the past couple of years. I know it's very macroscopic level description, so if you'd like to learn more details, you can connect me via email or LinkedIn. And my thesis is also publicly available through NC State University. And thanks again for watching!